So for this reaction, I'm not going to copy over, for this problem, I'm not going to copy over the diagram, but you should be looking at your book to see it. And so we have two different species that have a potential, we need to figure out the order of theirs, so that's NO and Cl2, and then once we figure out the order of each of those, we can figure out the rate law. So let's look at NO first. From experiment 1 to experiment 2, the amount of NO doubles times 2, and Cl2 is constant. And so now let's see how the rate changes. The rate is multiplied by 4. And so since for a doubling of NO, the rate goes up by 4, we know that the order of NO is 2. 2 squared. This squared being for second order. To figure out Cl, Cl2, we can look at the difference between reaction 1 and 3. So in reaction 1, we have the same amount of NO, that's constant, but we have double the amount in going from reaction 3 to reaction 1. And so let's see how the rate changes. Well, the rate goes up by 2. Also, goes from 5 times 10 to the negative third to 1 times 10 to the negative second. So since we have this direct relationship that every time Cl2 gets doubled, the rate gets doubled, we know that this is first order. And so with that information, we can write the rate law. The rate is equal to K times the concentration of NO squared, because it's second order, times Cl2. And that's our answer. Now, in order to find the rate constant, we actually have all this info. We can choose any one of the experiments. For instance, let's choose the first experiment. The initial rate is 1 times 10 to the negative second times K. Then the concentration of NO is 0.13 squared, and then chlorine is 0.2. And when you do that and solve for K, you'll find that that is equal to 2.95 inverse molar inverse second. And then finally, now that we have K, we can find a rate if we have this K and then 0.12 for each of the concentrations. So 0.12 squared times 0.12, and you'll find that that rate would be equal to 5.11 times 10 to the negative third moles per second.